Okay, good morning. Good morning, anyway. Today we would like to discuss on a famous and well-known concept in physics that has fetched the Nobel work in 20th century, and the effect is known as the Josephson effect of that kind. Josephson effect is one of the greatest effect discovered by the Josephson on some phenomena, particularly linked with the superconductivity. It's one of the landmark experiments of the 20th century. On the portrait, you can see a gentleman, a British physicist who lived in 20th century and who made a remarkable work on in physics, actually, particularly on detecting or identifying a kind of a motion of an electrons in a superconductor. Okay, see that the text goes in such a way you can also have the information of that kind, not a big issue, but what made him to think it off in a way where others can't expect that this type of a phenomena is a remarkable phenomenon. Josephson effect describes the transfer of some Cooper pairs. Cooper pairs means it is a pair of an electrons. Actually, I will let you know in due slides. The coupling of the macroscopic wave functions between the two superconductors via some kind of a weak link. Superconductors are the conductors where the resistance offered by the material for the flow of the electric charges, that is the electrons, is minimal, need not be zero, is minimal at the low temperature phenomena. Scientific community is trying to get the superconductivity or phenomena of superconductivity at room temperature. It is a hot topic going on across the world, actually. What it says that is that for a macroscopic functions, wave functions, between the two superconductors, some kind of a weak link they can call weak link. Some of the dependencies of such junctions are strongly related to the fundamental flux of the quantum. Flux means movement of some quantum, some type of a quantum nature from one position to another position. This gives an excellent possibilities for applications in measurements of science and electronics. Measurement of science means that is the parameters linked with the science. On the right hand side, you can see that the right extreme case, actually a block diagram showing that a single just one junction, they can call A and B, are the two superconductors which are joined, which are linked, which are brought together by some kind of a material that is a weak material. Weak means it should not be conducting, it should be an insulator of that kind, actually. A material like of the dimension of the C, for example, maybe of the order of nanometer. If you bring, there may be a possibility of the movement of the charges from A to B or maybe B to A that constitutes a current. This current has having a great effect in physics applications and also in the applications of several things else. What happened here? Josephson effect is named after the British physicist Brian Josephson. In 1962, he predicted a mathematical relationship or maybe a kind of a mathematical expression, they can call, that related a current and voltage across weak link, what you are expecting in a C. Weak link in the sense, if you bring the two semiconductors, sorry, not semiconductors, superconductors together and keep them with some separation, or if there is a called a media of non-conducting material or as an insulating material, certainly charges will move from one junction to another, either A to B or maybe B to A or maybe both, actually, by breaking something. That barrier is called the breaking of the barrier. That breaking of the barrier gives with some current. That current is an enormous current, actually. DC Josephson had been seen in this experiment prior to 1962, but had been attributed to these super shots. He knew of that one, but could not able to come to a conclusion. He expected in such a way that movement of migration of charges from a region to another region, he called it as a super shots in the science, like bullets which are firing from a gun at shorter durations, or sometimes it may also be known as the breaches in the insulating barrier. Region C is the insulating barrier, leading to a direct conduction of the electrons between the superconductors. Yes, it is a direct conduction. Even with the barrier, there may be possibility of the direct conduction. He could not able to come to a conclusion, actually. Right side, you can see that the text. The first paper which appeared in a international journal to claim the discovery of the Josephson's effect was by the two scientists, Philip Anderson and John Rowell. In fact, these two authors were awarded with the patents on the effect that were never enforced but never challenged by any scientific community across the world so far. Therefore, before Josephson's prediction, that is before 1962, it was only known as a single electron, or you can call it as a non-parity electron. Paired in the sense two, that is the Cooper pair what you're expecting actually. A single electrons individual electrons actually can flow through an insulating barrier, that is C what you are showing on the top, by means of quantum tunneling. There should be a tunneling they can call. This tunneling process they are calling it as a quantum, like a drilling. Maybe you might have seen that in metro stations while we are undermining of the metro, a huge machines will pierce through. That is also called a tunneling actually, tunneling effect. Here this tunneling we are expressing it in terms of the quantum tunneling. Josephson was the first to predict the tunneling of superconductivity, particularly in Cooper pairs. For this work, he received a great prize known as the Nobel Prize in 1973 in 20th century, where no one of you have won at that time. Being this, what this tunneling means. If two superconducting regions are kept totally isolated, what we call between the region A and B, each other, then the phases of the electron phase in the two regions will be unrelated. If the two regions are brought together, then they become a closed electron pairs, or you can call those pairs as the Cooper electron pairs, will be able to cross the tunnel gap, that and the two electron pairs waves, what we are expecting, will become a coupled wave the waves becomes coupled. As the separation decreases, the strength of the coupling increases. Means that is the distance of separation between the two superconductors, or the thickness of an insulated material which is isolating the two superconductors decreases. Certainly the strength of the coupling enhances. The tunneling of the electron pairs across this gap carries with a superconducting current, which was predicted by the Josephson and is called the Josephson tunneling. With the junction between the two superconducting, that junction is known as the Josephson junction. You can call it as a Josephson tunneling, Josephson junction, Josephson barrier, Josephson current, Josephson potential, which is leading to that. Like this, a superconductor, the gap which has a critical current, if a supercurrent, like a current which is flowing through a gap between the regions with a phase difference of delta psi, and it is related, it should be related with an expression IC, they can call current which is moving through that, IS must be equal to IC times the sine of delta phi, they can call, so that the maximum current flows across the gap when there is a phase difference of pi by 2, or when those two currents should be equal. Then this is a simple relationship. What happens is, see that the Josephson tunneling junction is a special case for very more general type of a weak link which occurs between the two superconductors. Other forms include the constrictions, or maybe a restriction, or you can call it as a barrier and point contacts, but the general form is a region between the two superconductors which has a much lower critical current and through which the magnetic field can penetrate. Let us remember up to this extent. I will explain the barrier, how it works actually. Okay, this is the overall view. This is the overall view, or you can call it as a preamble view of that kind actually. Here, what happens to make you an understanding? Right at top, there is a picture in such a way that represents in classical mechanics how that electrons must climb the tower, maybe a barrier tower of that kind. The potential hill, for example, this hill is known as a potential hill, appear on the other side. See that the charges moves up and goes down. This is the case. How your bicycle, a cycling will go actually. You climb the mountain and then go down the mountain on other side, or vice versa, to a great extent, whichever way the direction, not an issue of that kind. Okay, this from all sides. But what happens to the quantum mechanics? But quantum mechanics allows the electrons which with the less energy to tunnel through this barrier and appear on the other side. So rather than moving here, this it chooses a least path, it chooses a closed path, it chooses a minimal path actually, it is a closure path actually. This is a him. Means contrasting this to the classical over the barrier motion against the quantum through the barrier motion is the representation. What happened here? Consider a ball which is rolling from one valley to another over a hilly region. These two are called valleys. If the ball has enough energy to overcome the potential energy at the top of the barrier between each valley, then it can roll from one valley to another valley. This is a simpler way. Everyone accepts and also expects that. But this classical approach, or which is classical picture, and which is controlled by the simple law of conservation of energy, approach taught in beginning of the physics course for all of us, and you are well aware of it. However, if ball does not have enough energy to climb, for example, to cross over, for example, but whatever may be the energy which is available, which is enough for the kinetic energy to overcome this barrier, potential barrier, it will never roll from one valley to another. But the scientists found that there are possibilities of the charges on the other side of the valley. How it has come, how it has happened, in context to that, when quantum effects are taken into the effect, ball can tunnel through. This effect is known as the tunneling effect to the valley, even if its kinetic energy is less than the potential energy of the barrier at the top of one of the hills. Means to say, this tunneling is a quantum mechanical phenomenon when a particle is able to penetrate through a potential barrier which is having a higher energy than the particle's kinetic energy. At the same time, this is an amazing property or characteristic feature of microscopic particles which play an important role in explaining several physical problems such as nuclear fusion that occurs in main sequence of stars like sun. This is one of the example. How it has happened? Through the tunneling, through the barrier tunneling, in what we have that kind. It has an important applications in the tunnel diode, for example, TDs, and even quantum computing, quantum QEDs, they can call quantum electron computing of that kind. In addition, the principle of tunneling leads to the development of scanning tunneling microscope STM, which had a profound impact on both chemical, biological, and metal science research, which is happening. You might have heard that the STMs, the scanning tunneling microscopes, are used based on this tunneling effect, and where Josephson was the person behind it for its discovery. Being this, see the purpose. This is a simple thing what we want actually. Okay. What is the purpose of this one? To describe the Josephson effect and to show some consequences of Josephson effect, maybe in terms of some examples. To understand the effect of working of this squad. Squad is nothing but superconducting quantum interference devices, they can call, and to demonstrate their features. What happens? How they can do that? Right side some diagram has shown. Similar to that, let us see that how the description can go. This Josephson analyzed what happens at a junction between the two closely spaced superconductors. This is the superconductor 1 and superconductor 2 with a potential energy of psi 1 and psi 2. These are the wave functions which are representing from the quantum mechanical approach, which are separated by an insulating barrier of the order of about nanometer. Combine them, if you apply a potential, that what will happen? You will see that these are superconductors which are separated by a thin insulator of this kind. If insulating barrier is very thick, the electron pairs cannot get through. Means that is, if the barrier height is quite high, electron pairs which were formed between these two regions will not be penetrated through, which cannot be penetrated through. But if the layer is very much thin, of the order of a few nanometers, about less than nanometer of that kind, there is a probability for electron pairs to tunnel. To tunnel means to drill, to go through a channel actually. This effect later became a Josephson's tunneling effect of that kind actually. Besides displaying a broad range of interesting macroscopic quantum mechanical properties, this effect offers a junction known as the Josephson junction, which is having a vast survey of the possible applications in analog circuits, analog electronic circuits, digital electronic circuits, for example, like squad detectors, or maybe an oscillators, mixers, and amplifiers of all kind. Suppose how it works, we'll see that in a simpler way. I will not go into detail with the mathematical expressions. One can work on it, there is no issue. But here, as a landmark experiment, our intention is to understand the landmark phenomena. Suppose we have two superconductors which 1 and 2 can call, or superconductor 1 and superconductor 2, that are connected by a thin layer of insulating material. We define the quantum mechanical wave functions as psi1 corresponding to superconductor 1 and psi2 corresponding to superconductor 2. If that is the case, the state in the left and the right superconductors, where one can write the dynamics of the two wave functions, how that these wave functions can perform, which can determine the which can be determined by the Schrodinger equations, particularly coupled, because these two are linked actually. IH cross times del psi 1 by del t must be equal to, see, IH cross must be equal to mu psi because of the two wave functions which are coupled. IH cross del psi 1 by del t must be equal to mu1 times psi 1 plus mu k times psi 2. However, the same expression for the region 2 is IH cross del psi 2 by del t must be equal to mu2 times psi 1, psi 2, sorry, mu2 times psi 2 and plus corresponding to the k psi 1. See, k should be interchanged. Okay, k should be interchanged, or even psi 1, psi 2 should be interchanged. Here, k is a constant which is representing the coupling across the barrier. Okay, this is k is the coupling barrier, and mu1, mu2 are the lowest energy states in region 1 and 2. Because of this, what happens? There should be a strong relationship, a strong nonlinear current voltage behavior, or IV characteristics they can call for a change in the voltage, how that current behaves or how that current moves actually. Here, change in the voltage gives us the current actually, how that current changes in a circuit, current moves or the charges moves from region 1 to the 2 or 2 to the 1 actual behavior is our region for many different physical phenomena that we'll see now. Yeah. This is the one thing. This is the result, in fact, actually. This is the typical IV characteristics on right side. You can see that for superconducting tunnel, which is studied by Josephson and is known as Josephson junction. This is about 50 millivolt. This is about 1 millivolt of that kind. Here, what happens if you apply? You see that this is the rising, and as the potential rises, it increases very short to a great extent, becomes constant. Here there is no barrier. Here, because of that, this is a barrier thickness that you can expect actually. The charges move from here. Enhancement in the current will go up, but shoot up to a great extent. It increases abruptly. Means almost from 50 millivolt to about 1 millivolt if you're expecting here. This is how that. This is the the picture on the black diagram was done by the Josephson, and on bottom side we are saying that this is a recent developments or recent results which are obtained by many scientists while working on this Josephson. What actually here happens is that the scale of the vertical axis of the order of 50 microampere, okay, that of the horizontal is of the order of 1 millivolt. Okay, it means change the voltage by 1 millivolt gives you an current of the order of about 50 microamperes. The bar at about 0, V is equal to 0, V 0 represents the DC Josephson effect, while the current at larger values here is due to the finite value of the superconductor band gap, and which is not reproduced by any of the equation. Above equation means what I told the psi 1 to psi 2. This is here, it leads with the three effects. One is the DC Josephson, DC effect. Another one is the AC effect. The third one is the inverse Josephson effect actually. Theory part I'm leaving right now. It is not much required. Okay. If you are keen, you can go through, no issue. Otherwise, as being an experiment which served as the landmark experiment, how it worked, we will see that. This DC Josephson effect is a direct current crossing the insulator in the absence of any external electromagnetic field. Here, if you switch off this one, this is for AC actually. If there is no potential at all actually, okay, then Y into the turning. This DC Josephson current is produced, which is proportional to the sine of the Josephson phase. For example, I is equal to I naught times some sine of some angle they can call. Current can be drawn through the junction without any voltage drop as long as the DC current is smaller than the current actually. The phase difference will adjust according to the equation. I is equal to I naught times sine of that phi. AC, what will happen? AC Josephson effect is the one with the fixed voltage across the junction here because of this. Okay. The phase will vary linearly. It varies with the phase of the angle with the time and the current, which will be a sinusoidal AC with the amplitude. The junction's capacitive and resistive properties, which is modeled by several scientists based on their resistivity and capacitity, which were shunted at the junction model, now describes the DC characteristics. This is the one. This is for the DC. This is for the one. Sorry, this is for the DC characteristic. How it can happen of that kind. Inverse effect is the one actually with the microwave radiation, or maybe with the electromagnetic radiation. If you are submitting actually, sending actually with a single frequency, or if a single electrons are moving from one region to another region, it can be induced with the quantumized DC voltages across the junction of that kind. Because of that, how it has to happen, you see that it is a enlarged way. These are the superconductor 1 and 2. Here what I am showing here, the same case, superconductor 1 and 2. 1 and 2. This is a barrier. This is an enlarged image for you only to understand. What happens if you are interested to choose only between the two regions, X with some delta X, the barrier, what happens? The barrier thickness will reduce, and the tunneling process can happen. This is the representation of a Josephson's tunnel junction with effective barrier thickness of the order of about few nanometers, or about few angstrom of that kind. Actually means starts from this point, okay, it migrates from region 1 to the region 2, 2 to the 1 of that kind, between the two wave functions of that kind. How that analogy can be expected? Analogy of a Josephson junction in a magnetic field and light which is diffracted in a single slit, if you are expecting actually, this is the region 1 and region 2 what I shown. This is a magnetic field which is applied. Because of the magnetic field, if it is applied perpendicular to the current should be a perpendicular to the magnetic field, and what happens is that because of that charge carriers moves from left to the right of that kind, but magnetic field is perpendicular to this actually, towards the paper or towards the display, towards the board, or towards you of that kind. See, assume these are the two regions of the two superconductors. Because of these two superconductors, which are separated by a thin insulated material, non-conducting material, and if you allow the light here, what happens actually, critical current, if you are expecting the current against this field, actually if you are going changing the magnetic field coordinates here from magnetic field on either side, the flux reduces at the center point in the non-conducting material, not in a superconductor. The current is very huge. See that the peak actually. This is of the order of, in terms of the normalization, if you expect 100%, you are getting where it is of the order of less than 20%. From this 20%, it decreases to a zero value on either side. This is one of the beautiful result what he got out of it. Yeah, is another kind. The superconducting quantum interference devices, they can call superconducting quantum interference devices. SQUAD is most sensitive magnetic fluxes sensor currently known. Actually, how it works, the SQUAD can be seen as a flux to a voltage converter. Flux means that is the depending upon the charges, and it can be generally used to sense any quantity that can be transduced into the magnetic flux, such as electrical current or maybe voltage or position, etc. Here, this is the total current, and here, because of that, see that how that flux can change. Changing the flux can be accounted by making use of these things. The extreme sensitivity of this SQUAD is utilized in many different fields of applications, including biomagnetism, material science, metrology, not meteorology. There is the measurement, field of measurement, astronomy, and geophysics. But here, a SQUAD is a simple Josephson's junction, two junctions they can call, not two Josephs, two Josephson's junction in which are used in parallel. These junctions are used in parallel. That is how you are getting actually based on that. Instead of two, for example, here, if you use the magnetic field with the same case on the either side of that kind, analogy of a SQUAD in a magnetic field and light interference through two slits, for example. Instead of one, if you use the two slits here, earlier case is only one slit actually. If you use the two slits actually on either side, if the thickness of the insulator is quite larger, light will pass through that, and you may not find the difference between these two. Always see that the peak, the widening in the region of the current for a longer path, you are expecting actually this will happen. How you are expecting this? That how that IV characteristic which are shown at this point actually. Based on that, This is again same case, because these are with the different pictorial representations I'm trying to convince you in such a way. Left side, you can see this is the face what I told. Of course, cursor is there while copying. Don't get confused. Actually, nothing is there. This is the phase 1 and the phase 2 between the two regions of the phi 1 and phi 2. If the current is for a superconductor between conductor 1 and 2, and this is the gap. And if the current is quite larger in conductor 1 current, okay, or the number of charge carriers are more relatively, then current has to move from higher current region to the region of the lower current, higher flux to the lower flux. The difference should be super current can flow, which is directly proportional to the phi 1 minus phi 2. Of course, it can interchange also, where we can expect a complete circuit of that kind. What happens? These are the two superconductors. This is a formation of an electron pair, and here if it is a layer of an oxide or layer of any kind as a barrier, certainly it will pierce through, tunnel through. How it is happening? For this, you are applying a potential, let it be key, and one can able to measure, make the measurement of the current across the insulator. What happens? These Cooper pairs can pierce through and can form a wave function from region 1 to the region 2, or even from region 1 to the region 1 to 2, or region 2 to 1 of that kind. Is this, see that. Two wave functions I expected, what you could find with the density of the charge carriers of the rho 1 and rho 2, and the phi wave function is defined by psi 1 and psi 2, which can have the function square root of rho 1 times the e times I times phi. This is, see, this is the psi, this is the phi, this is the rho, this is the pi. They are all different things, okay? And how that? This is the constant potential barrier here. When it reaches the potential barrier, particularly insulating region, it drops abruptly. There is no barrier at all. Here also the drops abruptly. This junction makes us the current hues where the peak you can expect at this point of moment. Cooper pair of electrons, pair means always it should be production of the pair of electrons. That pair is known as the Cooper pair, and crossover of the Cooper pair charges from region psi 1 with the function psi 1 to psi 2 or psi 2 to psi 1. This is the scheme of the Josephson junctions, a thin insulator barrier maybe of the order of few nanometers, which separates the two superconductors, forms a tunnel junction. This junction is also known as the Josephson junction. The overlap of these macroscopic wave functions allows the tunneling of the Cooper pairs to move from one to the other regions. What happens here? Josephson himself has stated in such a way that a supercurrent could tunnel through an insulating barrier which are separated by two superconductors. Josephson junction is schematically represented by the two superconductors which are separated by a thin insulated barrier, which is shown in the figure. Fine. If the junction is biased with a DC current, for example, like what you are applying like a potential here, the voltage across it remains zero up to a current value called I naught, and then due to the Cooper pair of the tunneling through the insulator, the current is I must be equal to proportional to I naught times. This is the maximum, lowest current, minimum current with the sine of phi. If sine of phi is 90 degree, if it is perpendicular, it should be the maximum. If it is zero, certainly it should be. If it is about at 45 degree, you are getting 1 over root 2 times, that is 0.7, what you are expecting of that kind. This is called so-called DC Josephson effect, which occurred due to the overlap of the macroscopic wave functions psi 1 and psi 2 in the barrier region. These functions overlap. See the overlapping of psi 1 and psi 2 functions, how that they can go actually, how they can go. This is a huge number of applications. Yes, we'll glance through. Of course, this list is not exhaustive list. It is only a limited list. At least you can try to remember, or you can try to understand the phenomena. There are different types of Josephson junctions, which can include the phi Josephson junction, of which the pi Josephson junction is a special example, because there should be pi should be of different kind. A long Josephson junction you can call, and superconducting tunnel junction you can call. Either phi Josephson junction, long Josephson junction, and superconducting tunnel junction. They are all different types actually. Among that, a Debye bridge is a thin film variant of Josephson junction, in which the weak link, which consists of a superconducting wire with the dimensions on the scale of a few micrometers or less, was studied what we have got it. The Josephson junction, which is of a device which is used as a benchmark for its complexities. There are several applications where Josephson effect finds its advantage actually, and there is a wide usage. That is listed here, one or the other. One is the SQUET, that is the superconducting quantum interference devices, which are very sensitive, particularly magnetometers that operate via Josephson effect. Why? Because we need that type of devices in engineering and science, particularly for achieving a large current by the application of the small potential. Even in precision meteorology, the Josephson effect provides an exactly reproducible conversion between frequency and voltage. Because we must be directly proportional. Sorry, I must be directly proportional to V, or V is equal to I times R. Sorry, V is directly proportional to the I. Depending on the current, you can expect that how much that voltage can be developed within the barrier. Since the frequency is already defined precisely, and the practically the see like some kind of a standards which is known to the extent of the cesium source standard as an electromagnetic radiation, the Josephson effect was used for most of the practical purposes to give the standard representative of a voltage definition for an voltage, or the Josephson voltage standard they can call it. Okay. Single electron transitions are often constructed or restricted of superconducting material, which is allowing for us to use to be made of the Josephson effect to achieve the novel effects. The devices are called superconducting single electron transistors, they can call. The Josephson effect is also used for most of the precise measurements of elementary charges in terms of qubit or even other schemes where, in terms of the Josephson constant and one Klein constant, which is related to the quantum Hall effect, I can call. Similar to the Hall effect, what you studied, relation between I by V, there is a quantum Hall effect based on this Josephson junction. Josephson junctions are integral in superconducting quantum computing. It is a QED called, it is a very well-known technique now in qubits, such as estimation of the flux qubit or even other schemes where the phase and charge act as the conjugate variables. Superconducting tunnel junction detectors, they are calling it as an SDGs. You might have heard that BJT bijunction polar transistors of that kind. Okay, here superconducting tunnel junction detectors become a viable replacement for couple devices, CCDs, charge coupled devices for use in astronomy, particularly in telescopes and also in astrophysics from last several years. Few years means from last few decades, 1 or 2 decades of that kind. These are effective across wide spectrum from ultraviolet to the infrared. Means it is possible to detect all kind of radiation and even X-rays. Means getting a spectrum in X-ray or ultraviolet or infrared individually can be measured, but if the spectrum is coming from all the regions, is a difficult task. Therefore, the technology has been tried out with William Herschel telescope in SCAM instrument, which is the recent instrument sent for the measurement in space astronomy to a great extent. It is these applications, whatever we mentioned, is not limited to a great extent. This is not the exhaustive list. This is only a simple list or sample of the list of that kind. Try to learn. This is a novel experiment. This is a novel phenomena worked out by Josephson for finding the large number of applications, particularly in superconductivity. This is the one case where I stop at this point actually to a great extent to try to learn, and thank you for sparing me your valuable time on this Sunday.